Um, I'll vanish temporarily as well, yeah.
Good afternoon and welcome to the 2023 Beale lecture. My name is Seb Hargreaves. I'm the Executive Director of the Operational Research Society. I took over from Gavin Blackett at the beginning of last month, and I'm glad to see you all, so many of you joining our Beale lecture this afternoon. Before I hand over to our President, Gilbert Owusu, I just want to share some items of housekeeping with you. Just bear with me. You should be able to see my screen. There we are. So just to remind everyone that we recommend you position the speaker in the top right-hand corner of your Zoom screen so that you can see all the slides as we move through the presentations. Please use the chat function that you have to send us any messages rather than raising your hand with the hand icon. And please, if you do have any questions for the speakers during the presentations, please use the Q&A function. And you can also vote for the questions by upvoting them. So we'll cover some of the questions after each of the presentations, and I'll help to facilitate that. The session will include time for Q&As after each presentation, as I've said, and we are also recording this session, and it will be available shortly after the event on our website. So, without further ado, I will hand over to the Operational Research Society's President, Gilbert Owusu, to introduce the speakers. Gilbert.
Thank you very much, Seb, and a big welcome to all our attendees to this year's Beale lecture. This year's lecture will be delivered by Professor Robert Dyson. Professor Dyson's talk is titled Operational Research Through 7 Decades. This year marks the 75th anniversary of the formation of the OR Club, the forerunner of the OR Society, and the 70th anniversary of the Operational Research Society. Professor Dyson's talk is timely and will provide us with the opportunity to reflect on the role that OR has played in improving decision-making using both soft and hard methods. As is customary for this event, we'll have a talk by our doctoral award winner before the Beale lecture. And this year's doctoral talk will be given by Dr. Jake Clarkson. Jake is a postdoctoral researcher at INRIA. Before joining INRIA, he completed his PhD in 2020 on optimal search for a hidden target at Lancaster University. Jake will present the subject of his doctoral research entitled Optimal Search in Discrete Locations, Extensions, and New Findings. Jake, over to you.
Thanks, Gilbert. Yeah, I'll just share my screen. Okay, yeah, so hopefully everyone can see that. So hi everyone. I'm Jake Clarkson, as Gilbert said. I'm a postdoc at the INRIA Centre on the Côte d'Azur, and I'm going to talk today about my PhD, which I did at Lancaster University at the Story Centre for Doctoral Training, and it was funded by the ESPRC. So I was supervised by Kevin Glazebrook, who was also at Lancaster, and Kyle Lin for the Naval Postgraduate School in California. Now, as you can see from the title, this thesis is going to be about search, and this is a physical search for a lost or hidden object. And as we'll see throughout the talk, the thesis basically takes a very simple search problem, which was solved rather elegantly over 60 years ago, and makes two extensions to it, the two-speed extension and the intelligent hider extension. But before I get into any details, let's talk about some quick motivation. So why is searching for hidden objects important? Well, in many situations, there can be huge costs involved in conducting searches and severe consequences if these searches fail. So, for example, on the right, we have marine salvage, and it can be very expensive to send a diver down to the bottom of the ocean. So we want to make sure that we're doing it in the optimal place. And then also on the left there, we have search and rescue, where there are human lives at stake. So we've got ample motivation there. So I'm going to start by describing that classical search problem solved in the 1960s, and alongside its simple and elegant solution. And then later, I'm going to show how our work builds upon this classic problem with those two extensions. So what do we have in this classic problem? Well, we've got just one missing object, which doesn't move, which is hidden in one of n discrete locations, which I'm going to call boxes. So just imagine you've got n boxes on the table in front of you. There's an object hidden in one of them. You don't know which one, but you want to find the object as soon as possible by making successive searches of the boxes. And I'm going to run with this example at the bottom here of 3 boxes throughout the talk. Now, each box has 3 pieces of information. So there's 3 bits of notation to remember, and all of these are known to the searcher before the search. So the first is a prior probability P, and this is just the probability with which we believe the object is in each box at the start of the search. So for example, in box 1 down here, P1 is equal to 0.5. That just means before we make any searches, we believe that the object is in box 1 with probability 0.5. And note that these probabilities, they sum up to 1 over all the boxes. So there's no chance that the object could ever be elsewhere. The second, well, we're going to allow for the concept of the boxes being messy. So we're going to give, so basically what that means is that you may search the box where the object is, but not find it. And in order to do this, we're going to give each box a detection probability Q. And this is just the probability that the object is found on a single search of that box if it is located there. So for example, if the object is in box 1, any time I visit box 1, I find the object with probability Q1 equal to 0.4, and I overlook it with probability 0.6. And the upshot of this is that I may need to search the box where the object is multiple times before I actually find it. And finally, the third value is just T, and this is just the time that it takes to search that box. And just to reiterate, all these quantities are known to the searcher before the search. They don't have to learn them or anything like that. Now we're going to say that we must fully search each box before moving on to any other box. And so what that means is I'm not going to allow any partial searches. So you can't search half of box 1 and then half of box 2 or anything like that. We're also going to assume that each search fails. So we're going to be constantly asking ourselves the question, where would we search next if we hadn't yet found the object? So what this means is that a search policy is just an ordered infinite list of boxes to search, like this example here. And in this example, the first search is of box 2. If that search fails, then the second search is of box 3. If both the first 2 searches fail, then the third search is of box 2, and so on and so on. And we just want to find the search policy that finds the object as soon as possible in expectation. Now, as I alluded to earlier, it turns out that this is pretty easy to do and was first done in 1962 by Blackwell. And there were subsequent proofs afterwards. And also in 1979, Kelly showed that the Blackwell solution was equivalent to the famous Gittins index solution to a multi-armed bandit. But don't worry, you don't need any knowledge of multi-armed bandits to be able to follow the index solution, which I'm going to describe now. So what do? Well, for each box, we calculate a Gittins index, which is given by this expression here. And we see it's just a function of the 3 box parameters, P, Q, and T, and also a function of this M, which is just the number of times that box I has been searched already. Now, the Gittins index summarizes the value there is in currently searching that box. So what we do is we calculate Gittins index for all the boxes, and then we search the box with the largest index, greatest value, and that is the optimal box choice. So in the running example I had below, well, at the start of the search, m equals 0 for each box, so we're just calculating PQ over T, and we see that the largest value is for box 2, so it's optimal to search box 2 first. Now, the form of this Gittins index is quite intuitive. So remember that it summarizes the value there is in searching a box. So let's think about what it is that attracts us to searching a box. Well, it's a large chance of the object being there at the start of the search, so a large P. So P is on the numerator. It's a large chance of finding the object if it is there, so a large detection probability Q, also on top. A small time cost T, which is on the bottom. And we also want a small number of previous visits M, because if we think in a Bayesian manner, the more times that we've gone to a box and not found the object, the more evidence that is that the object isn't actually there. So it's a very intuitive measure. But now let's come back to this problem at the bottom. So as we said, we're going to search box 2 first, because that's what our optimal Gittins index tells us to do. We're going to assume that this search fails, because if not, then we found the object and we can go home. So this is going to increase M2 from 0 to 1, and it's also going to decrease the value of the index of box 2. And it makes sense that, that this index goes down, because now it's less likely that the object is in box 2, as we've just searched there and not found the object. Now we look at our indices again. And now we have a tie. Now, by Gittins' rule here, it's actually optimal to search either box. So let's just say arbitrarily that we're going to search box 1. And if we carry on in this manner, so searching a box, recalculating our indices, taking the max, etc., we will increase our M's and we will generate this optimal sequence here, which I'm going to call a Gittins search sequence. So in summary, the optimal solution to this classical problem has a very simple form, and it's also very easy to implement. The final thing I want to say on this simple problem is that remember, after one search, we've had a tie between boxes 1 and 3, and we just arbitrarily chose to search box 1 next, and then hence box 3 afterwards. But it would have been equally optimal to search box 3 first and then box 1. So we see that this tie actually spawns another optimal Gittins search sequence, the same as the one above, but just with these 2 searches here highlighted switched. Now you might think, well, why do we care? This is just another optimal policy. But the answer is that we will care with the second extension of the intelligent hider that I will talk about. So do bear this idea of ties and hence multiple Gittins search sequences in mind. But first, I'm going to talk about our first extension. And in this first extension, we consider 2 ways to search each box. A fast speed, so we're going to give each box a fast speed and a slow speed. And I'm going to use these colors, red for fast and blue for slow, throughout. Now, when deciding which speed to use, we have a trade-off between speed and accuracy. The fast search is quicker, but there's more chance of missing the object if it is in that location. Now, our motivation for this extension was twofold. First, advances in technology has seen an increase in the use of robots and drones for searching, and these may have multiple search settings or search modes. And secondly, there are many applications where there are naturally multiple search agents available. For example, a bomb squad may have the choice between searching in a vehicle, which is faster, so has a smaller T, or going on foot with sniffer dogs, which is more thorough, so has a larger Q. So just to formalize this extension, we're now going to give each box 2 detection probabilities and 2 search times, with the fast lower than its slow counterpart in each. And as we can see, you can see here at this example at the bottom, now each box has 2 Qs and 2 Fs, 2 Ts, sorry, with indices S and F. So now, each time we make a decision, we have to choose both a box and the speed at which to search it. So this means that a search policy now becomes an infinite list of 2 tuples, and there's as shown here. So in this example, the first search is of box 3 using the fast speed. If that fails, the second search is of box 2 at the slow speed, and so on and so on. And when we started thinking about this extension, the first question we asked was, well, how much does the single speed solution help us here? And that's what I'm going to explain now. So for each box, I'm going to fix a sequence of speeds, which is going to determine the speeds at which I search that box. So for example, if I fix this sequence here for box I, then the first time I search box I, it must be done at the slow speed because S is first. Then the second time I search box I, it must be done at the fast speed because F is second, and so on and so on. Now, with these speed sequences fixed, we take the choice of speed away from the searcher. So now they only have to choose a box, which is just like a single speed problem, which we know is solved by Gittin's index. And it follows that in the world where the speed sequences are fixed to A1 to AN, so we have a fixed speed sequence for each box, then a Gittin's index policy is optimal. And what the index looks like, so whether we use the fast or slow QT, that depends on the next speed in the fixed speed sequence for that box. So for example, again, suppose that box I has this sequence up here. Then the first speed is slow. So before the first search of box I, we form the Gittin's index with QS and TS, since they correspond to the next speed we have to use, which is slow. However, after the first search of box I has been made, the next sequence in the speed sequence is fast. So between the first and second searches of box I, we use QF and TF to form the index. And we also just multiply by 1 minus QS here, as we'll already have made 1 slow search of box I. But the key takeaway from this slide is that the single speed Gittin's index solution reduces the challenge in the 2-speed extension to just finding these optimal speed sequences. Because once we have them, we will know which detection probability and search time to use in the optimal index. Another way to think about this is a Gittin's index policy is still optimal in the 2-speed extension. We just don't know which detection probability and search time to use to form the index. But we do have some results which determine these optimal speed sequences for certain boxes. So our first result concerns when the slow speed dominates. And it says that if I have a box where the detection probability divided by search time is greater for slow than for fast, then that box is always optimally searched at its slow speed, no matter the other boxes in the problem. So for such boxes, the optimal speed sequence is just full of slows, and the index is always formed using the slow detection probability and search time. Now, what about fast? Can I just flip this inequality here and then fast will dominate and I'll cover all boxes? Well, the answer is no, not quite. We do flip this inequality, but we need to multiply by 1 minus QS to be able to prove that it's always optimal to search fast, in which case the optimal speed sequence is full of Fs and the index always formed with the fast detection probability QF and fast search time TF. So where do these theorems lead us? Well, let's label the boxes 1 to n. Then they allow us to, the theorems allow us to partition our boxes into 3 subsets. So I'm going to define S as the boxes which satisfy the slow theorem, so where we know it's optimal to always search slow. F as the boxes which satisfy the fast theorem, so where we know it's always optimal to search fast. And H for those boxes that satisfy neither theorem, so the optimal speed is unknown. Now, if H is empty, then we only have boxes in S and F. So we know all the optimal speeds. So our problem is actually solved by a known Gittins index policy. So we're done. If H is non-empty, then our problem is still solved by a Gittins index policy, but the problem is we don't know which. So we need to come up with a strategy for choosing speeds for boxes in H. And for this, we turn to heuristics, which is what the H stands for. So the first thing we thought is, well, let's try the most simple thing. Let's just pick a speed for each box in H and always use that speed for that box. And that's what I mean here by single speed heuristic. And the performance of this heuristic is actually pretty good. In a numerical study with 2 boxes, both of which are in H, the best performing single speed heuristic over the 4 possible is within 0.1% of optimality in 95% of sample problems. But we thought, well, we have the ability to search these boxes in H at both of their speeds, which we just aren't using with a single speed heuristic. And we'd also noticed that the optimal policy can use both speeds for boxes in H. So we thought, well, can we take advantage of this ability to search at 2 speeds within a heuristic? And the answer is yes. And we did this by considering 2 types of benefit to searching a box in H, which we call immediate and future benefit. So what are these benefits? Well, immediate benefit is the chance of finding the object right now, so the next time that we search that box. And for boxes in H, fast is better at this per unit time because the fast detection probability per unit time is greater than the same value for slow, just by the definition of that slow theorem that I introduced earlier. Future benefit, on the other hand, is about learning about the object's true location after a failed search, because this is information which is useful in the future. And we measure it by the rate at which our belief that the object is in a box drops whilst we're searching it. Now, for boxes in H, it turns out that slow can be better at future benefit per unit time when the box is close to the set S. So if you remember the condition for being in S, it's where this inequality is close to being an equality. Otherwise, fast is better. This is an interesting observation because Q over T just defines how good a mode is, a search mode is in the single speed problem. But here we see that slow can actually beat fast on future benefit, even when its Q over T is less than that for fast. But anyway, what do these observations of immediate and future benefit mean for a heuristic? Well, in the otherwise case here, so when fast is better at both benefits, it just makes sense to search fast. So no matter the value of P dash, which is the current belief that the object is in my box, so the posterior for those Bayesians. So no matter the value of that P dash, I should always search fast, as demonstrated here. Now, in the other case, when the box is close to being in S, and when fast is better at immediate benefit, but slow is better at future benefit, we're going to ask ourselves, well, how does the value of P dash, current belief that the object is in the box, how does that affect the significance of these 2 benefits? Well, remember, immediate benefit concerns actually finding the object. So this is more significant when we actually believe the object strongly to be on our box. So it's more significant for larger P dash. But on the other hand, future benefit concerns learning that the object is elsewhere. So this is more significant when the object is not in that box. So it's more significant for smaller P dash. So this motivates a threshold policy. When P dash is close to 1, we search fast because in immediate benefit is more significant. And when P dash is small, we search slow because future benefit is more significant. And this threshold here, P hat, we just calculate this using the formula we have for immediate benefit and future benefit. So this picture here actually summarizes our 2-speed heuristic. For each box in H, we try both of these. And we find that this 2-speed heuristic actually performs very well. So in the same 2-box study, where the best of all the single-speed heuristics was in 0.1% of optimality, we find that in 95% of problems, we find that our two-speed heuristic is within 0.01%, sorry, in 95% of problems. So that's our first extension to the single speed problem made by the thesis. Now I'll talk more briefly about the second extension. So we're dropping two speeds now, but the second extension to the original classic problem, this sees a lost object replaced with an intelligent hider who wants to remain undiscovered for as long as possible. So in other words, wants to maximize the expected search time. Now, this extension opens up new applications where what we're looking for is actively trying to avoid being found. So like a computer hacker or an intruder. Now, this problem is actually quite well studied in the literature, but the results are limited either to cases where there's only two boxes or to cases where each box is searched in time one, or even both. And so our aim was to get some results for the fully general case of arbitrary n boxes and arbitrary search times. Now, the key difference to anything that's been in the talk so far is that these prior probabilities that the object is in each box, so this P1 to Pn, well, these are now chosen in secret by the hider, so they are not known to the searcher. And this causes an immediate problem because the searcher can no longer enact a Gittins index policy, because this is at the bottom is the form of the index here, and it depends on P. So the searcher, therefore, needs to think like the hider. And this takes us into the realm of game theory, two-person zero sum to be precise, with zero sum since the hider and searcher are in direct conflict. Now, this branch of game theory has a neat classification discovered nearly 100 years ago by von Neumann. However, this application to search has an issue. So a strategy for the searcher is a search sequence. And recall that this is an infinite list of boxes like this one here. So therefore, the searcher has an infinite number of strategies to choose from. And this limits the extent to which we can apply this clean standard game theory. And it also makes the search game hard to solve. So we certainly had ourselves a challenge. So we started, like von Neumann, by defining an optimal search strategy eta star to be a minimax strategy. And that's one that minimizes the expected search time if the hider hides in the worst possible box for that strategy. So in other words, the minimax strategy does best in the worst case scenario, or does best if the hider discovered what our strategy was and exploited it. Now, as is common in game theory, eta star must involve some random behavior to avoid being predictable by the hider. And in this case, eta star will actually choose randomly among several search sequences. And in fact, by combining von Neumann's game theory and the Gittins index solution to the classic single speed problem, we deduce that eta star must actually choose amongst these Gittins search sequences against an optimal hiding strategy, which will denote P star. And recall that there are many, even infinitely many, Gittins search sequences against any P star due to those ties between indices. If you remember my example before, where we had a tie between boxes 1 and 3, which spawned another Gittins search sequence, and we could run into arbitrarily many ties. Now, to find an eta star, an optimal search strategy, 3 questions remain, which our work attempted to answer. So the first one was, well, does one exist? Because the searcher has an infinite number of search strategies, the general game theory does not even guarantee the existence of an optimal search strategy. But thankfully, we managed to prove that one does always exist, so we're not wasting our time trying to find one. Secondly, well, we see, as we see from the above here, eta star chooses from Gittins search sequences against P star. So how do we find an optimal hiding strategy P star? Well, we devised an optimality test for any hiding strategy, which consists of solving a game where the searcher has finitely many strategies. And this is a lot easier than when the searcher has infinite strategies, and we can just use finite linear programming for that. And finally, so let's say, okay, yes, so we know a P star. Remember that eta star then randomizes over a selection of Gittins search sequences against P star. But then how do we choose this selection? Because theoretically, there could be an infinite number of these Gittins search sequences to select from. Well, we show that the searcher can actually limit themselves to a finite subset which satisfy a nice property. The nice property being that any tie is broken by a fixed order of preference. And once we have this selection, the optimal randomization over the finite set can then again be found by linear programming. So just to summarize, so we started with a simple search problem with a simple index solution found in 1962. Our first extension was to add a second speed, so we now have fast and slow. We still have an index solution in this case, but the challenge then becomes which speed do we use to form the index? Our main findings were conditions where just one speed is used for a box, so we can throw the other away and that box just becomes single speed. And then outside of these conditions, we contributed a two-speed threshold type heuristic that performs very well. Now, our second extension was to replace the lost object with an intelligent hider. The problem now is that we can no longer form the optimal index since it depends on the hider's strategy. And this took us into the realm of game theory. Our contributions were to prove the existence of an optimal search strategy, and then we also had several results which facilitated the calculation of optimal strategies actually from both players. So that's all for me. Thank you for listening. Thank you to the OR Society for giving me the chance to talk here today. And thanks to all at Story and Kyle and Kevin for all the support that they gave me throughout this PhD. And just here's some references. The first two, those solutions to the classic problem, and then a list of publications that we got out of this PhD below. So yeah, thank you again.
Thanks so much, Jake. What a fascinating insight into optimal search in discrete locations. So we have a couple of questions in the chat. Firstly, Jake, is there a trade-off between P and Q and the size of box if the latter is defined by the searcher?
Is there a trade-off between Q and the size of the box? Yeah, I think what we were thinking more with Q. I see what you mean. That I think if the size of the box was bigger, then we would increase the T. So imagine if you had a really big area. I don't know, like imagine you had a really large area. You've got two really large areas, and one is a forest and one is like a desert. Then we would assume that both had a large T because both have a lot of area to go across. But the Q would be a lot smaller for the desert than for the forest. Because in the desert it would be a lot easier to spot something like, I don't know, say a survivor of a disaster or something would be a lot easier to spot in the desert than in the forest. So in those areas we would have large T's for both, small T for the forest, small Q for the forest, large Q for the desert, and then the P would be more just depending on your belief about where. So if it was survivor of a disaster, it might depend on where the disaster was. If it occurred nearer to the forest, or say, like in marine salvage, if a ship went down, the closer to where the last known location would be a larger P. So P is more on belief of where this person might actually be. And then, then the Q and T depend on the T on the size, and then the Q on the terrain that you have to search, I would say.
Great. Thanks, Jake. Lots of appreciation in the chat for you. So well done for that. I've got another question here. Very interesting and seems big step forward, but how would the approach change if there was more than one searcher, for example, search more than one box at the same time?
Yes, that does then become more difficult, because obviously if you had say you wanted to use this index theory, if there was a clear winner for a box that you wanted to go to, and there's just one searcher, it's obvious to send the searcher to that box. But then if you have a second searcher, then suddenly you think, well, would it be best to send them there to help, or is it best to cover more area at the same time? And yes, that does make things a lot more difficult, because you can't really just assume that the first searcher has finished, because if the first searcher has finished, then that gives information about that will update our beliefs about where the object is as well. There is some literature which I looked at when I was writing my literature review, I think in the 70s and 80s, that looked at when there were multiple searchers, but it wasn't for two speeds. So they looked at where rather than just one search to allocate, you had a number. So that approach has been looked at in the literature. But I imagine that then also putting two speeds into that could be done, but we probably wouldn't get as nice theory as we get for our problem.
Great, thanks, Jake. I can't see any more questions that have come through at this stage. If anyone's got any more questions, please pop them in the Q&A. Just a reminder as well for everyone to please share your experience of this year's Beale lecture on our social media. You can use the hashtags #ThisIsOR and #BealeLecture as well. I think we've got a question actually from John Croker. I'm not sure whether we can get John on to ask that or whether he's able to put it in the Q&A. Right. Whilst we just figure that out, is John there?
I am, but I didn't have a question for you. Sorry.
That's okay. No worries, John.
Sorry about
nice
that.
to see you. That's okay. I've actually got another one in as well here. So do you have any thoughts on how you define the size of each box? For example, you could have larger boxes that take longer to search or more smaller boxes that take less time to search. Is there an optimal strategy for allocation of spaces?
Well, yes, then that does become quite difficult. I guess you would need to have the queue, the detection probability being the same throughout. You would probably want to split into different sorts of terrain. But then that would become there is there's some literature as well on continuous search spaces. So where rather than discretizing into boxes, they just assume that it's like a map and you can move throughout the map. Just walking through it with a drone or something. But there isn't quite as rich of a theory there that you can get from the discretization. But regarding that, I mean, I guess the smaller the boxes would be better, but you'd want to have a continuous the same sort of terrain, so you could share the same value of Q, I guess. But then one other thing that this work doesn't cover is that if travel times, so this problem becomes a lot harder when you introduce travel times. So it assumes that each box you can reach all the boxes at the same time, and there's no times in, say, traveling from box 1 to box n. Or once you do introduce that, which again has been looked at in the literature, so you're almost searching on like a network type structure. Then this particular problem, even when it's discretized, can become a lot harder when you put that in. But that's definitely an important consideration.
Great, thanks, Jake. Another couple of questions. Follow up to the multiple searches question. What do you think are the important characteristics of the problem in applications?
To the multiple searches question. So sorry, what was that question again? What do you think?
What do you think are the important characteristics of the problem in applications?
I think the main thing that we found, I would say, that we're going into practice is that there is this hidden advantage that the slow search has. So in the single speed problem, the Q over T is what classifies everything with a search mode. But when we did the fast against slow, we found that this slow has this extra future benefit advantage even when its Q over T is smaller. So I would say that's almost like a key takeaway that could be taken into applications, because obviously in applications you've got there's a lot more complicated stuff than can be neatly summarized into this problem. But one of the key takeaways could be that searching slow, if you have the time to do it, it does have an advantage in that there's this better information gain. Unless the fast mode does dominate it a lot, when those Q over T's are similar, slow does have this benefit, which isn't always apparent. So maybe if you have the time to do it, to search slow. But then of course, if you have a deadline that you have to search by, so you only have I don't know, say an hour left to complete the search, then, which is something that we don't consider, we just consider minimizing expected search time, then you might want to do fast just to be able to get that search in before the deadline. So that's kind of, I think, how fast and slow would trade off. So I think those are some sort of key messages to take into applications.
Great. Thanks, Jake. And a final question, nice one here. We're aware that you run the project in collaboration with the Naval Postgraduate School in California.
Mm-hmm.
Did you get the opportunity to apply the model on naval use cases?
We didn't, unfortunately. I got the opportunity to go, which was very nice, to visit Kyle over there. Yeah, we've not had any. I mean, I've had also had the opportunity to discuss, because at the Naval Postgraduate School, so some of the academics there haven't past military experience. So I had the opportunity to discuss some of the findings with them and present them to them, and that led to some interesting discussions. But I don't think we quite, well, if they have, they haven't told me I got into anything practical. But yeah, so I was just very grateful to go there, to go and visit there, to be honest.
Fantastic. Thanks, Jake. Really fascinating talk. Thanks very much for
no, thanks a lot again, and
spending
thanks
the
for the
time.
questions, and thanks to everyone for listening.
Brilliant. Great. We're going to hand back over to Gilbert to introduce our next speaker. Gilbert.
Thank you very much, Seb, and many congratulations, Jake. Well-deserved recipient of this year's doctoral award. Well done. Let's move on to the highlights of today's event, the Beale Lecture. We are very honored to have a truly distinguished speaker for this year's Beale Lecture. So Robert Dyson is Emeritus Professor at the University of Warwick. He is widely recognized internationally for his contribution to OR. Robert has published extensively in the fields of cutting and packing, stochastic programming, financial modeling, strategy support, data enablement analysis, and performance management. He was the president of the OR Society from 1998 to 1999 and was elected a companion of OR in 2007. Robert was also the chair of the Committee of Professors of Operational Research from 1995 to 1997. Please join me in welcoming Professor Robert Dyson, our speaker for this year's Beale Lecture. Over to you, Robert.
Hi, everybody. Hope you can hear me. I will share my screen, I hope. Yeah, it's good to recognise so many people when I look down the list of names. The title is Operational Research Through 7 Decades, although it really ought to say in 7 decades, because the 7th one is the current one and we aren't through it yet, are we? I'm pleased to give the Beale Lecture because I knew Martin Beale very well. In the 60s and 70s, I was mainly interested in mathematical programming, so I came across Martin in many occasions and heard him speak. Also, with SciCon, where he worked, we got a SRC Case Award for a PhD student, and we jointly supervised Robert Ashford on his PhD, and Robert completed in 2 years. And somewhere in the 70s, there was a conference, a Euro conference in Amsterdam, and the conference dinner was held on boats on the canals. And there were tables of 6, and we, Dorothy and I, my wife, had dinner with Martin and his wife, and Stanley Zients and his wife, and it was a very memorable evening. So I relate well to Martin. He was, of course, not only the leading mathematical programmer in in one of the ones in the world, but also a fellow of the Royal Society. And very few operational researchers have become fellows of the Royal Society. Just some preliminaries. Operational research, modelling, experimentation, inductive and deductive reasoning approaches to problem solving. And of course, the phrase operational research was coined in World War II. The modelling that we talk about are models of the search models, as we just heard about, linear mathematical programming, queuing models, forecasting, revenue management. None of those were used in World War II. In World War II, the operational research was about experimentation and inductive and deductive reasoning. And the phrase operational research was coined because although it was about military operations, it was scientists working alongside the military. And so it was operational. I'm also mentioning software because it appears throughout the decades, a complete approach from problem structuring to decision without the development and solution of a quantitative model. The models here tend to be quantitative models, but in software they don't use quantitative models. And problem structuring methods, these are the specific methods that enact software. And it's argued that it's scientific because it involves inductive and deductive reasoning. Well, the first decade I want to talk about is the 60s. I was at Liverpool University in the early 60s. This was the time of the Mersey beat and the Beatles, and the Beatles used to play at the Cavern in Liverpool at lunchtime, and a friend of mine at university was at school with Paul McCartney, and he used to badger me to go down to the Cavern at lunchtime, and I used to say, no, I'm too busy doing my pure maths or whatever. And said, oh, go. And Paul bought me a drink, and he kept pestering me. And the Beatles, the top of the Mersey hit parade now, he said one day, and I said, big deal. And guess what? I never went. But I'm leaving Liverpool. But I did meet OR at Liverpool University, however, because in my final year we had a course on operational research techniques, things like LP and assignment problems and transportation problems and queuing models and so on. So I got my first taste of operational research at Liverpool University in the early 60s. In '64, I joined Pilkington Brothers, who were then the largest private company in the country. And not long before I joined Pilkington's, they'd invented a new way of making flat glass, the float glass process. And it made all the other ways of making flat glass obsolete. So everybody in the world had to license the Pilkington float glass process. The float glass was a continuous process, 24/7, but they only wanted to cut it up during the day, and that's the area that I got involved in, is how best to cut the glass up. I'll talk a little bit about that in a minute. While I was at Pilkington's, Lancaster University were running a PhD program for people in industry, and I signed up to that program, and along with a number of other people, including John Ranyard, who many of you will know. I was fortunate in that I was based in Pilkington's in their R&D laboratory, so I was fortunate to be able to align my research, my work at Pilkington's and my research for Lancaster very well, and that meant that I was of the group of people doing this non-residential PhD. I was first to finish, and I think that's partly because I was in a very favourable position through my workplace. I joined the society somewhere in the mid-60s, and there was a big debate going on about professional membership. The society, of course, founded in the 50s, was entirely practitioners. There weren't any academics, as far as I know. Well, there might have been one or two, but largely it was a society of practitioners. And in the 60s, the practitioners wanted to professionalize a society. They thought it should be a profession like accountancy or whatever. And they came up with the idea of a register of practitioners. And this caused a lot of debate in the society. And I think there were two things about it. One was the process. People objected to the process. The idea was that the senior members of the society would go on to this register of practitioners, and then they would decide who else could join them there. And also there was another concern that maybe the way they were describing it would define operational research in a particular way, and that was also seen as problematic. Jonathan Rosenhead headed the campaign to stop this proposal for register of practitioners, and indeed he was successful. And I'll return to that topic later on. Going to the Pilkingtons, as I said, we had all this glass coming down the production line, floating on tin and cooling and being cut off into stock sizes, which had to then be cut into smaller sizes, smaller rectangles. And there were a number of cutting machines, but the one in particular, the high throughput one, was producing rectangles for the multi-trade. So we had a stock size cut into smaller rectangles for the multi-trade, and the bits at the end could be waste, and there might be some waste down the side. And typically we'd be dealing with 100 order sizes and perhaps 4 different sizes in stock to cut up from. And you could cut the stock sizes in different ways with the machine, and each different way was a cutting pattern. And you could define this problem, you could define as a linear program where you want to minimize the amount of stock you use to hit the order sizes. And the linear program is each row is an order size. So we've got 100 rows, 200 of these, 150 of these, and so on. And every different cutting pattern was a column. And with 100 order sizes and 4 stock sizes and the different configurations, you can imagine that there were thousands and thousands of different cutting patterns. And although our computers filled rooms in those days, it couldn't solve an LP as big as that. And Gilmore and Gomery came up with the idea of column generation, where you start off with a solution to this linear program, you make up a solution, and then you have a side problem, a knapsack problem, which generates a better cutting pattern to add to the solution and replace one of the existing ones. And you iterate around, and this column that gets generated, because each cutting pattern is a column. This column that gets generated is the same one that you would have chosen from these thousands and thousands if you'd had them all in the model. So that was we had to then, of course, adopt that approach to our particular circumstances, and we addressed 2 other interesting problems. One was the sequencing problem, because if we started cutting an order size, it might occur over 3 or 4 different cutting patterns, and we want them to follow in turn, so that we didn't have part orders cluttering up the warehouse. We could take our LP solution and we could sequence it using a travelling salesman problem, a travelling salesman algorithm. But unfortunately, we could only sequence 20 order sizes with the capacity, with the computing capacity at that time, and we had 100 order sizes. So we had to produce a heuristic which would produce good cutting patterns in the appropriate sequence. So it wasn't quite so efficient on the stock used, but it gave us a better sequence. It wasn't a bad solution, but not as good as it would have been if we could have sequenced the whole 100 sizes. The other thing we did was use our LP model and a search routine to find the best stock sizes. And in fact, finding the best sizes to put into stock turned to be as effective as important as getting the best cutting patterns. So those were various problems that we addressed during my time at Pilkington's. And sorry. Oh, this is the 70s. I seem to have lost the 70s. Here we are. So now we're in the 70s. Sorry, I can't see where it said. Oh, I know why, because I'm covering this up in my. Oh no, never mind. In the 70s, they published a couple of papers on the work at Pilkington's. The actual PhD thesis was embargoed for 7 years because Pilkington's were very nervous about their intellectual property. But they allowed me to publish 2 papers, and this one, Mike Chambers was my supervisor at Lancaster, and this one was awarded the President's Medal, which at that time was awarded to the paper that was the second best paper in the year after the Goodeve Medal. Nowadays, of course, the President's Medal goes to an application, and I think we could have made a pretty good submission to under the current rules as well. Well, in the 70s, I also got involved with stochastic programming briefly, and I'll say a little bit about that. And I first came across software. I went to an operational research society meeting, I think at Shell in the 70s, and this was perhaps the first meeting in the society on software. And it was being presented, and I think Jonathan Rosenhead might have been doing a presentation where he put up a problem, a wicked problem, as we have in software, and he then put up an integer program to and showed how it was completely useless in solving this problem, and then went on to talking about problem structuring methods. And I, perhaps inadvisedly, at that time I knew quite a lot about integer programming, and I pointed out that the integer program that he put up was a pretty hopeless one. I could think of a much better formulation. And also, you can use mathematical programs in an exploratory way. You don't just have to go for one optimal solution, which is how it was being presented. However, that comment wasn't well received by the audience. And in the 70s, I did some work, began to get interested in strategic planning, which hadn't got a bad name then, or strategy support. And we went me and the family, we spent 3 months in the Netherlands on study leave, sabbatical leave, and I got access to 2 organisations in the Netherlands, the Regen Dinkel Water Authority and Axel, a chemical company. And I got access to study their planning systems, and in particular I was interested in how different stakeholders participated in the planning, and that got written up in long range planning. Now the stochastic programming, as you see, I've been working on cutting stock problems in the 60s and early 70s, and I decided I'd do something different. So I thought, with my degree in mathematical statistics and knowledge of mathematical programming, I ought to be able to make some progress on stochastic programming. I got some funding to do some work and was joined by Gillian Swaits to work with me. And we were playing with an oil refinery model, which to be used for medium-term or capacity planning, which was a linear program with stochastic parameters. And our interest was, of course, to use the model, not just to not to schedule things today or this week, but to look ahead to how the model, how things would work out if we tried out different capacities in the medium term. We'd have to decide which capacities to go for now but they wouldn't come into play for 3 or 4 years or longer in an oil refinery. And of course, a lot of uncertainty would have crept into the system by then. Now you could just put in, so we're using the model to help evaluate these different capacity proposals. And you could use the model, you could put in best estimates, the best forecast for the stochastic parameters and get an evaluation that way. But we were interested in an evaluation if the uncertainty turned against us, if you like. So we have some linear constraints, crude availability, capacities, and so on. And then we have some constraints with uncertainties. And in the simplest case, let's suppose we just had a couple of uncertain demands, and we were interested in what happens if these demands don't turn out as we would like. So we constructed what we call a plausible region on the uncertain parameters. I say in the simplest case could be just a couple of right-hand sides here, and if they were normally distributed, then you could define a plausible region bounded by an equal probability function, which will be an ellipse, but in 2 dimensions, so that there'll be 95 or 99% of the density inside here and the rest outside there. And our model would do the best we could, maximize over our variables the best we could, given that the uncertain parameters were doing the worst they could. So we were getting a worst case analysis to go along with any other analyses. And this, of course, is a nonlinear function. We had to add this nonlinear function to the model. And you know, for more complex things, you could have random parameters in other parts of the model. You could have more complex things. So we worked on that. We produced 3 papers. I presented a couple of presentations at conferences, but nobody seemed interested. So when the grant ran up, we gave out. Some years later, robust optimization was invented, and it had a lot in common. Our work in the 70s had many features in common with the later robust optimization. This is one of the papers that we produced. Some of our plausible regions meant that we had a non-convex problem. So we had one of our papers was about a global algorithm for minimax solutions to a stochastic programming problem. Now we're in the 1980s, and talk about 3 things here. I was fairly busy in different ways, but I did some work on socio-technical systems analysis, which I'll say a little bit about. I'd been to Tom Lupton gave us a seminar at Warwick on socio-technical systems analysis, which I found very interesting. And not long afterwards, one of my ex-students, who was the manager of a peat bog, asked me if I could help him. We're trying to improve the output from the peat bog, and wondered if I could advise on how best to do that. And I thought a socio-technical systems approach might be a useful way of doing that. I'll come on to that in a minute. I then did some work on strategy support, and also began work on data envelopment analysis. Socio-technical systems analysis. I can't see the top. Sorry. Oh. Sorry, I can't read the top of the screen. But at the top of the screen, I don't know if you can read, it says, or on the peat bog, a case for qualitative modelling using socio-technical systems analysis. The manager of the peat bog, essentially using peat in those days for compost was not seen as a bad thing. It holds the water, and you're not burning it. So it wasn't seen as a bad thing in those days, it is now. And the manager he got a limited budget and he didn't want to, you could imagine having collecting lots of data and doing a simulation model and doing quite a thorough study. And he didn't have the resources or time or inclination for that. So, which is why we adopted a qualitative approach. And in socio-technical systems analysis, you identify performance measures, which in our case were the output of peat. You identify relevant variables involving stakeholders, such as storage capacity and weather. You identify interactions and causal relationships between variables and on-performance measures. Then you assess the strength of the relationships qualitatively and assess the manipulability or controllability of the variables qualitatively. And then you can formulate a strategy based on the variables with high manipulability and beneficial impact on performance. And we had in the article, which is published in JAWS, we had this information in tabular form, but later on I produced some software, and with software the model, which was produced a diagrammatic form of the problem, and this is the diagrammatic form. Around here we have the various variables. Output is our performance measure in the middle. The letters here are whether these variables are easy to manipulate or not, high manipulatability, low manipulatability. And the stronger the link between the variables, the thicker the line. So we got and this can then be a diagram that we can help us talk about the solution as we do in software. And in this, and we're advised here to focus on the variables with high manipulatability and also on the relationships that are strongest. So if we throw away the others, we come to a simpler diagram. And from this, we came up with 4 suggested things to do. One was to, instead of cutting blocks of peat, to rotivate to get the peat. One was to improve the internal transfer. One was to improve our stock holding capability. And of course, another was to increase the labour. We'd need to increase, many of these things required more labour, which is shown here in these diagrams here. In fact, of these 4 things, the bottom 3 were implemented, but the top one wasn't. And the reason for that was that they were a bit worried that if they started rotivating on the peat log and it didn't work out too well, they'd find it difficult to go back to their original process of cutting. So they decided not to risk doing the rotivating, but they did improve internal transfer, stock holding, and increase the labour. And this article, Operational Research on the Peat Bog, actually won a prize from the society called the Pergamon Prize, which might surprise you because it's not, I don't think they're listed anywhere, the Pergamon Prizes, but the journal at that time was published by Pergamon Press, owned by Robert Maxwell, and they give a prize for the best applied paper each year for a few years until we moved to a different publisher. So strategy support, we started work on strategy support. I've done a little bit of work in the 70s, and I got some money, and John Foster joined me working on continuing the empirical research I'd started in the Netherlands. And we got access to about 10 public and private sector organisations. And we focused on 2 things. One was, one of the things we focused on was what is an effective planning process. And we ruled out a simple goals achievement approach because of the uncertainty in the future. And we wrote a couple of articles which appeared in eJAW on talking about effectiveness in strategic planning. And we then also explored the relationship between the participation in the companies that we looked at, the organisation we looked at. Yeah, and we explored the relationship between participation of the various stakeholders and the effectiveness of the process. And we got an article exploring that relationship, which was published in the Strategic Management Journal. At the same time, so that was quite an interesting piece of work that we did. At the same time, I started on a course in OR for strategic planning with Rolf Tomlinson, the professor at that time. We began it in the 80s. It was bumbling along with myself and Rolf. And then it got a boost when Francis O'Brien joined some time later. And we supported it with different books, and I'll talk about the end book later on in the 2000s. But the course involved a whole range of hard and soft topics, lots of different lecturers over the years. Myself, Francis, and Maureen Meadows were the sort of the key teachers for many years. In the middle of it, but we had Alberto Franco did work, Richard Ormerod, John Friend did some sessions for us, and so on. Giles Indle, John Moorcroft, Martin Dunn. So over the years, it's had many. We taught it first of all to undergraduates, and it's still being taught. And I think Frances is now still holding the fort, and she has something like 250 students on the course. But we also had versions of it to the MSCs and the MBAs, but those aren't being run anymore. I think it's partly lack of resources and partly the way that the MBAs look at what they want in their course and what they don't want in it. So I then move on to I started work on data envelopment analysis in the 80s. This came about in two ways. Rolf Tomlinson actually gave me an article, the original DEA article by Chand and Cooper, which has had something like 44,000 citations. And so I spent some time studying this article, and about the same time, Ross Tristram, who was the Deputy Director of the Audit Commission, got in touch with me and said, have you heard of this data envelopment analysis stuff? He said, because we're interested in it. The Audit Commission, their remit was to find best practice in local authorities and spread it throughout the system so that the best practice will get transferred throughout the system. And to be able to do that, of course, they had to be able to identify where the best practice was. And in the local authority community, they had ideas where the best practice was, but Ross said, well, why don't we try and have a parallel data-driven approach to finding the best practice? Let's try data envelopment analysis. So I got my colleague Emmanuel Thanasoulis to join me on this venture, and we started working on data envelopment analysis. Briefly, what it is, it's a way of where you've got a lot of units, local authorities or local authority departments or schools or bank branches when there used to be bank branches. Then you can set up a model where you define, first of all, you define efficiency of each of these units as the weighted sum of outputs over the weighted sum of inputs. You can set up a fractional programming model for each unit in turn, whereas the variables are the weights. You allow free weights. You want units to be able to have different weights because they might have different values to other units, and that's more easily explained when we come to the school idea. So the objective function is a ratio, and the constraints are that the efficiency of each unit shouldn't exceed 1. So you have a constraint like that for every unit. This is a fractional program, which of course you can easily convert to a linear program. And when you solve it, you solve one of these for each unit, and it will come out to have an efficiency of 1 if it's an efficient unit, or less than 1 if it's not. So here, in this little example here, these x's here are the efficient units by solving allowing them to choose their own weights or giving them their best weights. And they define an efficient frontier, and that efficient frontier envelops the inefficient units, and these distances give you an idea of the extent of the inefficiency. So we use this, and so, for example, supposing I've got a simple 2-output illustration here. This might be, if these are schools, this might be academic success up here, and this might be music and performance and cultural and social sort of dimensions. And here you might have a school that aims pretty well exclusively to get people into Oxford and Cambridge and the Russell Group or whatever, and doesn't waste too much time on music and stuff like that. And here you've got the Paul McCartney School of Performing Arts, which is all about this and does a certain amount of academic work. And these are all deemed to be efficient because they've got different missions, and the weights allow them to be efficient even though they're very different. And then inside here we've got all the other schools. Now, when we did our work for the Audit Commission, our first analysis of the 100, I don't know how many local authority departments we had, came out with fairly good discrimination. We came out with about 8 efficient departments and lots of inefficient ones. But one of the efficient ones was Liverpool. And this caused a little bit of consternation at the Audit Commission. They didn't believe that Liverpool could be efficient. And the reason it was efficient, or it came out efficient, I'm not saying it isn't efficient, the reason it came out efficient was that because it can choose its own, it got the best favourable weights. And in Liverpool, they had the highest number in the country of people who were unwilling to pay their local taxes. So they spent a lot, so they put a lot of weight on chasing people for their taxes, which is quite a reasonable thing to do, but they put 0 weight on collecting the money from everybody else. And this raised the issue of whether having this total flexibility of weights, allowing the weights to be virtually 0, was perhaps too generous to individual units. And we explored the idea of weight flexibility and restricting weight flexibility. And we produced an article on this, reducing weight flexibility and data and data analysis, based on the Audit Commission work, myself and Emmanuel, and that went down very well with the DA community. It's got about 1,000 citations, and a lot of work was done in that way. Sorry, here we go. I'm having trouble with moving my slides on. Right, thank you. I'm recovered. Well, I'm now moving into the 1990s, and data and development analysis work gained apace at Warwick, and I return to this issue of professional membership of the society. Because at Warwick during the 90s, all these people at different times during the 90s, not for the whole 90s, although I was there for the whole 90s. Emmanuel, who started off with me, was there for most of the 90s. Then Victor Podinovsky joined us. Andreas, who was one of Emmanuel's PhD students, became a member of staff. Estelle Shale joined us, and Jim Storbeck, an American, spent a year or two with us. So we had 6 members of staff all working on DEA in the 90s, and we had all these PhD students. Most of them were either my PhD students or Emmanuel's. I think Joe Coughlin was Estelle's. And we worked with, Emmanuel was particularly interested in regulation of water utilities, working with the water regulator, and perhaps he ought to go back and do some more work with them. We worked with banks. Anna worked with a Portuguese bank, and Joe worked with a UK bank. We worked on schools, we worked on primary care, perinatal care. And the topics we looked at, we've talked already about weight flexibility, but getting the balance between complete freedom of weights and some restrictions on the weights. Discrimination, of course, when you have multiple inputs and outputs, the more you've got, the worse the discrimination. So that's an issue we looked at. We looked into alternative perspectives. We looked into stochastic frontiers, Marquist indices, and all kinds of things. So there was actually a massive DEA operation in the 90s, and somebody somewhere in the world did a simple calculation for each institution working on DEA, did a simple calculation of how many papers they'd published and how many presentations they'd made at leading international conferences, and what it came out either first or second in the world, which perhaps isn't surprising when you see all these people. All the PhD students were encouraged to present at international conferences, and they always presented to us first. So we had a seminar series going on with typically 8, 9, 10 people. So it was a very good experience working with all those people in the 90s. The other thing in the 90s, I mentioned in the 60s, there was an attempt to introduce a register of practitioners, which failed. And that became rather an acrimonious thing. In fact, a number of people left, set up their own fellowship of operational research in the 60s so that they could have a professional membership. The society was prepared to go down that route. So there was a breakaway group. So this was a bit of a running sore throughout the 60s and 70s. In the 90s, the society returned to this, and a new proposal came forward. I think Lynn Thomas chaired a group to come up with a new professional membership proposal, which he thought might satisfy, because there was increasing pressure from some parts of the society for some sort of professional membership. So a new scheme was proposed, which hopefully would have got over the problems related to the first one. And it was put to the society, and in fact it did win a majority vote. But unfortunately, to get established, it had to hit a higher threshold than a simple majority, and it didn't reach the higher threshold. So that, of course, went down very badly with the people who wanted it. They were in the majority, but they couldn't have it because of the rules of the society. So when I became, I think that happened in my year as president-elect of the society. I became president of the society, and one of the things I proposed to do was to try and revisit this. And the council were in favour of us revisiting it. So I set out to lead the development of a fellowship scheme for the society. And the fellowship scheme, many of you will be familiar with it, but that we have 3 categories: fellow, we had at the time 3 categories: fellow, associate, and associate. And then later on, Val Belton had the bright idea of letting students in for free on the bottom room called candidate associates. So we now have 4. And the fellow scheme, and the principles that I put together were that there should be this should be an inclusive scheme, not one of these where you have a small number of fellows, which are the the really senior people in the society, but you should have an inclusive scheme where anybody could aspire to being a fellow. And the requirement was significant record of achievement extending over 10 years or more. It was available both to academics and practitioner achievements, but academics had to engage with practice, show that they engage with practice through projects or consultancy, and practitioners must show some of their work in the public domain through conference or SIG presentations. And that scheme was put to the society, and it did get through the higher threshold and is now in place. There was also momentum behind it, but unfortunately a lot of momentum was lost because it was decided to go down an online system for joining this, for applying for this scheme, and the online system wasn't very good. In fact, for example, you couldn't go back if you wanted to alter something you'd put into the system earlier. You couldn't go back to alter it, and a lot of people actually got fed up and never completed it. So that was unfortunate. But the other great thing about it was, though, is that the fellowship, which had been a breakaway group, closed down, and we're happy to see that the society got its own scheme. So that took the problem off the agenda, which was a good thing. Down to the 2000s, did some work on strategy support and became an editor of the European Journal of Operational Research. Strategy support was 2 sorts of strategy support work. One was work that I did, or we did, me and others did within the university. I was a pro-vice chancellor during this period, and we had a university steering committee that used to meet every Monday morning, except in August. And it was chaired by the vice chancellor, and had the pro-vice chancellors, senior administrators, and so on and so forth. So this was a senior management group of the university, if you like, and it was agreed that we'd have a workshop. We'd do a SWOT analysis on the university, and I facilitated it. SWOT: strengths, weaknesses, opportunities, threats. I was very conscious that some of these people are quite forceful individuals, as you might expect. So I was, as a facilitator, I thought it very important to make sure everybody contributed to the deciding on the strengths and weaknesses and so on. Of course, once you've done the SWOT, once you've got your strengths and weaknesses and opportunities and threats, you take a combination of these to come up with ideas for new strategies. And we came up with a whole list of ideas as things that we might do. And then we had a voting system to decide on which were the most important ones. And in fact, it turned out to be very timely because the university, after we'd done this, and of course it was a learning process for everybody involved, right across the senior parts of the university. And soon after this, the university got given about £11 million to spend. And so we were well equipped to have ideas of how best to spend it. The money came from the funding council, I think. But not only that, we did some work within the business school. Howard Thomas was the dean. He was keen on these sorts of ideas. And Alberto was working on computer approaches to this facilitation. And he wanted to suggest that we use SWOT analysis alongside a PSM. And he facilitated a number of workshops, which were useful, again, as a learning exercise. We also did some scenario planning workshops on internationalization, which is one of the many roles I had at that time. And one of the specific things that came out of that was to launch an international business degree. We had joint degrees with the with the language departments, but he wanted one that was more balanced towards business. And in fact, Francis O'Brien took over this was established. Francis Bryan took over directorship of it, and she was carried on for many years, and particularly enjoyed the summer schools, where all the students who were dispersed mainly throughout Europe, met together at either Disneyland Paris or Venice for a summer school, and Francis enjoyed leading on that process. The work with the university was published in the European Journal of Operational Research, and that's been fairly well cited too. So I've had ups and downs with citations. The stochastic programming was ignored by the stochastic programming community, perhaps rightly so, and the OR in Peatbog was ignored by everybody. This got quite a lot of attention. We had during the 90s, during the 2000s, we had a group meeting regularly at Warwick to discuss strategy support, or on strategy. There was myself and Francis, Maureen Meadows, Alberto Giles, and John Moorcroft and Jim Bryant were visitors, had visiting appointments at Warwick, and we used to meet on a regular basis to discuss it, and decided we'd go for a book. We spent a lot of time looking at developing ideas for a model, a process model of the strategic development process, and this was to become a framework for the chapters in the book. And the model had sub-models to do with direction, creation, rehearsal, where you rehearse strategies and implementation, and a lot of feedback looks. So it was quite a complicated model, which is why I'm not showing it. And it became a framework for the chapters, and everybody here was authors of chapters, and everybody here was, these were the other authors. And these are the sorts of topics, these are the kinds of topics that we had, and topics that were also in the courses that we were running at Warwick. The bottom, there's one particular chapter where I worked with Fernando Oliveira, and we wrote a chapter comparing decision trees, robustness analysis, and real options, which have all got some common, there's some commonalities between these three approaches to decisions. And we thought it was a really good chapter. Unfortunately, nobody's ever read it, but never mind. So in 2006, I became an editor of the European Journal of Operational Research. EJOR covers, it's a very big journal. It covers very broad in scope, covers all OR, management science, analysis topics, including software and interfaces with other disciplines. I've put including software there because the American journals, operations research and management science, wouldn't publish software, and Omega stopped publishing software papers. So there was only EJOR and JORS who were willing to publish in this area. EJOR gets typically these days about 3,500 submissions per annum, and its authors are not only the topics broad, but the authors are broad too, from business schools, engineering, maths, so on, and also with the interfaces from economics and finance and computer science, or got computer science there. It's very large, 2 issues a month. Developmental, we like to, if we thought there was good material in an article, we like to give people 2 or 3 chances to improve it rather than reject it out of hand. And although it's a very large journal, it nevertheless scores highly on the quality impact factors. Although there are some business school deans who, because it's large, write it off as being a quality journal, but the quality impact factors point to something else. I was the 4th editor when I joined. There are now 6 editors, and all making independent decisions. So it's different structure to most. This is a structure it started off with 3 editors, and it's continued in that way. One of the editors, which covers the softer side of OR, which is myself from 206 to 220, and Mike Yearworth from 220 onwards. And these are some of the popular keywords. We covered other topics as well, of course. So to 2010s, I continued eJAW editing right the way through the 2010s and got interested in the founders of operations research. And there was Graham Rand drew my attention to this. He was writing 2 of the chapters in a book about the founders of operations research. And there was a book launch at the Informed Charlotte conference in 2011, which Graham and I and other people were at. And I went to the book launch and actually bought a book, which I then read cover to cover. I find it a very interesting read. These are the founders. I won't go through them all, obviously, but they're mainly Americans. There are a number of Brits here, including Martin Beale, 1 or 2 other Europeans, but mainly Americans, and they're all men, which says a lot about how things have changed since that time. And the book is called Profiles in Operations Research, Pioneers and Innovators. And I was reading this book, and most of these authors, in fact, are mathematical modelers. And but yet, when I was reading it, I kept seeing connection with software in what in the description of, in the profiles of these mathematical modelers. And I was chatting to Francis O'Brien about over coffee one day, and I was mentioning this and thought, well, why don't we sort of research it properly and have a look? So we did. So first of all, we had to decide what software was. So we looked at what the pioneers of software said it was, and we got these characteristics of context, process, and content. Wicked problems, stakeholder involvement, facilitated workshops, diagrammatic models. And these are just the problem structuring methods, which are, but they're there if you want to look at them. And we found 2 things. First of all, these are the software pioneers: Colin Eden, John Friend, Peter Checkland, and so on, Jonathan, Jim Bryant. And these are a subset of founders were direct influences of these people's works. And some are not surprising. Akoff, Churchman walked away from operational research because it went too mathematical. So a number of the founders were the direct influences of the software pioneers. But then we found that there were many other hard modelers, mathematical modelers, who seemed to have soft tendencies. Bellman, noted for his dynamic programming, was concerned with qualitative features. Gass worked on LP and extensions, recognised the involvement of multiple stakeholders with multiple objectives. Little, key queuing person, recognised the place of different stakeholders in the decision process. Gomery recognised multiple stakeholders. Vassonier used Gazinto diagrams, input-output diagrams, to show a pictorial representation of materials requirements to communicate to key stakeholders. So many soft things amongst the hard ones. So we came up with some conclusions, not too surprising. I'm nearly finished. Software pioneers influenced a subset of the founders. It were influenced by a subset of founders, was a much wider group of founders, often characterized as hard or mathematical modelers, aligned with many of the software characteristics. So there was strong evidence, both from the work of the founders and from definitions of OR, that software is indeed a legitimate subset of OR. And that's important because there are still a lot of deniers of software out there. And one of the editors-in-chief of operations research said he would never publish a software paper, for example. And now you recall that the early software people threw hard models out of the window because they couldn't solve wicked problems. But in recent years, we've seen mixed hard and soft modelings, which indicates that hard models can indeed have an important decision support role in resolving wicked problems. And as an aside, it's in the paper and in the book, but not talking about it. But the proponents of software and the founders were all heavily engaged in practice, leading to key modelling and process developments. Many of the models that we know today, they weren't there. They had to be developed, and they were developed by the founders attacking a problem and inventing a model to help solve the problem. So we're to the 2020s. Ease your aging in decline. I was still taking papers up till the end of 2020, but then I stopped taking new papers and handed over to Mike Newworth. But I continued to deal with the ones in the system, and there are quite a lot still in the system, of course. In fact, I've nearly finished. I've just got one left to deal with. And in the 220s, our paper on the founders, the software and practice, the contribution of the founders of operations research, was published in the American Journal of Operations Research. So that's it. These are just the papers that we've come to before. So that's of course, there's another few years left in the 2020s, but I don't think I've got too much left in the tank to do much more. Thank you very much for listening.
Robert, thank you so much for giving that lecture today. What a interesting insight into your career in OR and the history and indeed the 7 decades of operational research. Thank you so much. Just looking to see if we've got any questions that have come through. You've definitely stimulated a lot of conversation and comments and discussion in the chat, so thank you for that. We did have a question around the production of bagless vacuum cleaners, but I'm pretty sure that is for a different Mr. Dyson, perhaps.
Yeah, he's a nephew of mine, yeah.
A nephew of yours. Okay, I wondered if there was. Yeah.
Well, we could be connected. There is a rumor. It is said there was a woman cattle thief up in the north, and it's said that 80% of all Dysons have a common gene from this woman cattle rustler. So maybe James Dyson and I have a common gene. I don't know.
Quite possibly. I've got a couple of questions actually that have just come in through the Q&A. Given the operations research editor's antipathy to soft OR, it is to your credit that your founder's paper was published there. What reaction to the publication did you have?
Well, nothing much from the Americans. Well, it's early days, of course. It's not been out too long, but it's beginning to build up some citations, but it's nearly all from people who have got soft tendencies. So I wonder if I fear it may not have made as much impression as we'd like amongst the software deniers. But of course, it is good evidence for people who want to claim that their work should be taken seriously by other journals. Whether anybody is going to be brave enough to submit a software paper to management science or operations research, I don't know.
Great, thank you. A question on here looking to the future. So despite not having finished the 2020s, what are your views or forecasts about the next decade in OR?
Well, I suppose that clearly analytics and artificial intelligence so on are becoming key things generally, not just in OR. Now, I'm slightly, well, I think we've got to be careful about that because, of course, the algorithms and everything are built on purely historical data, usually built on historical data. And of course, if you're looking at the wicked problem or the strategic end of things, then you're leaping into the future when relying entirely on the historical data isn't always a good way forward. You need more creative ideas, and I wonder if we might lose some of the creativity if we're not careful. So I think that's something for us to be aware of.
Thanks, Robert. I've got a hand up from Jeff Griffiths. I don't know if Jeff's got a question. I can come to Jeff if he's there and wants to ask a question. Are you there, Jeff?
Yes, can you hear me?
We can, yes.
My question to Robert is, as he knows, I'm a mathematician, and a feeling
I hold
is...
the polls against you, Jeff, yeah. Well,
My question is, do you think that the mathematics which often appear in journal papers is really out of place in the general sort of interest of operational researchers?
Well, I think it's quite difficult, isn't it? Because if very mathematical papers, and for most of us, they're not that easy to get your head around unless you're actually researching in that particular area.
Exactly. Yeah.
So the general operational researcher would probably not get much out of a mathematical paper unless it happened to be right in the area that they were interested in.
Yes.
I think that's a problem. Whether papers can be presented more accessible, I don't know. With more use of diagrams and so on, I don't know. Maybe they could.
Mm-hmm. Thanks.
Thanks, Jeff. I've got a question here around some lovely comments again. And do you want to comment on how the application areas have changed over the period, Robert?
I don't think I'm best placed to answer that. Maybe some practitioners in the audience might be
okay.
More. With the application. Well, I mean, some of the, I guess some of the problems, things like scheduling oil refineries and all, some of the historical problems, they still exist. But of course, once if they've been thoroughly sorted out, then there's nothing new for the academics to deal with there. On the other hand, you do get the impression sometimes that people forget about ways of doing things effectively. So that maybe there's always the chance for practitioners at least to reinvent the wheel in some cases. The one thing that is of interest, I mean, was being mentioned to me from Fran Ackerman, was about this issue of grand challenges, all the big problems of the world, and whether really we've got to find some way of being able to use something useful there. Been a lot of papers produced about COVID, for example. Climate change is a massive problem. How do we? Is there some modelling that could be done to work out how we can sort out our sustainable energy in the country? How much electricity we're going to need? Where does it come from? Is there some modelling there that could be done usefully? There probably is modelling going on, I'm sure. So maybe addressing these grand challenges is something that we need to pay more and more attention to.
Yeah, it leads really nicely into another question, which I think we probably answered it really, but what's the biggest, thorniest or messiest problem that, given no constraints, you would like the OR community to tackle? Is it that environmental issue you mentioned?
Yeah, I'm thinking. Yeah, I think it would be the environment. I mean, I get quite worried about. It seems to me, if you look at the political debate in this country, when one of these environmental conferences come up, it's all over the news. Everybody talks about it, and then they forget about it. Then it goes away. So if you look at Rishi Sunak's five priorities, he doesn't mention climate change anywhere, I don't think. So I think it's very worrying that climate change isn't at the forefront of everything. It's the biggest problem facing us, but there always seems to be short-term other things, pressing problems that people deal with. And I think we could be in danger of, we really might well have gone past the tipping point if we're not careful.
So it could be a real opportunity for the OR community maybe to look at that. Great. We have a request to see again the slide characterizing soft OR, the one beginning with the wicked problems. I think it's about fourth from the last. I don't know if you're able to pop that one back up. Possible.
No, sorry, I've gone too far.
Is it
this one?
I think that's the one. Yep. Thank you.
Yeah.
And then there's a lovely question here about knowing what you know now, what would you teach differently to the students of the 60s, 70s and 80s?
Well, I did teach differently in the 60s. Well, I didn't teach in the 60s. In the 70s, I taught mathematical programming, and I'm sure that it's important. I'm sure it's important that that's still taught and by other people. I mean, at Warwick, we've got people working in those areas and teaching in those areas. But I think teaching much more about, continuing to teach about how you address problem structuring and the softer end parts of OR, I think it's very important. And I think it could be well argued that, any course that's an application course in OR ought to have soft OR in there, because stakeholders and things are very important. So it ought to be in there, and maybe in some of the I think when people who are doing mathematical modelling, who are doing it, it seems to me would be well advised to take on board some of the systematic ways that soft OR people approach problem formulation, and that's I think that's one of the ways that one of the attractions of what we wrote was about that, about the fact that hard people who were doing models, very valid mathematical models, should be aware of the context that they're working in, and systematically look at the role of stakeholders and so on, and that certainly will help them in implementation. And also, if you're talking to stakeholders, of course, you need to be able to explain to them what's going on with your diagrammatic models.
Great, thanks, Robert. We're drawing to a close, I think, but we've got I just want to bring to members' attention a few things that my colleagues have been posting in the chat. There is a networking session that's following the Beale lecture this afternoon, with the details in there if you'd like to join that virtually via the Zoom link that's in the chat. And just to draw everyone's attention to some upcoming events and activity, we've got a simulation workshop down in Southampton coming up on the 27th to 29th of March, and also a call out for around our awards as well in there. So they're all in the chat. Again, lots of lovely comments coming through, Robert, from your lecture today. So thank you for that. I don't think we've got any more questions. I'm going to hand over back to Gilbert to just finish off as well. Karen's just reminded me we've got a webinar Wednesday next week too. So pop that in your diaries if you're able to join us for that. Gilbert, over to you.
Thank you very much, Seb, and thank you, Robert. Very insightful talk. Your work over the 7 decades have clearly demonstrated that both hard and software methods are required for effective decision making and helping us to realize whatever outcomes we desire, both in industry and academia. Thanks again to Jake, our doctoral speaker, and to all our 110 attendees. Many thanks for making the time to join us, and very much appreciate your engagement with the presentations.
Thank you.
In the chat. Yeah. Special thanks to Karen, Caitlin, Seb, and UR Society staff for the brilliant delivery of today's event. Thanks again, and I'll bring this event to a close.